Okay, so I'll skip introduction. Thank you for the introduction. Great to be here. But I go to the talk immediately because I know I'm going to be late, so I try to immediately jump to the content. So this is a talk that I prepared for a keynote I gave a Coda Spy 2 weeks ago. So it's still a work in progress, and it's still a work in progress in the sense that also I'm trying to fit more and more stuff and then cutting stuff out because it doesn't fit. So I intentionally and unintentionally left out a lot of stuff from this talk. It was a bit maybe too ambitious at the beginning. I wanted to try to cover a bit of the history of all research in malware, which is in 1 hour, well, a bit tough. So there are many ways to cover this sort of history. You can do it from an industrial point of view. I mean, search for talks from Nick Ponen, for example, online, excellent stuff. You can cover more like, the development of malware, more the underground part, also very interesting. But since I'm in academia, I wanted to cover the research. And I think there are already a lot of other resources that cover the other angles. So here we focus on research. And research on malware starts in, University of Southern California, and in particular in the lab of Edelman. Okay, so in this case, we had a PhD student of him, so from cryptologist. We would not maybe expect a malware start actually from a crypto person, but that was the case for the first maybe 10 years. A PhD student wanted to study the theory of self-replicating code. That was not invented by himself. I mean, there are papers dating down to the 60s on replicating automata, but that was the first time in which someone tried to formalize what is a self-replicating code. In this particular case, a malicious code. It was named virus for this, of course. Obvious analogy. This is the definition. We don't have time to enter in the definition, but it was already interesting because the definition is not a simple formal definition of virus is a definition or a viral set. So there was already this concept of the fact that there could be multiple variants that when this code self-replicates, that you need to detect all of them, or you want to detect all of them. Anyway, not much time to enter into it, but it's important the fact that in this first work, we had the first research question that we ever had about malware research, which is it possible to write a Turing machine program that in a finite time can tell whether a sequence for a given Turing machine is a virus or not? So we all know that the answer is clearly not. That's probably one of the most known theoretical results in computer security, and probably also one of the most misquoted results. But anyway, so here Cohen was able to prove something, diagonal proof similar to the outing problem, that no, it's impossible to write such a generic virus detector that can detect any sequence of Turing machine code to be a virus or not, so self-replicating code. So now for the rest of the talk, I will use this sort of metro map to describe more or less this main, according to me, research area that we have in malware and try to pinpoint some of the, the results that we had. So we start with this one. This is the first paper, Computer Viruses Theory and Experiment by Craig Cohen. Interesting the fact, already I found it cool, that he wrote the paper without his advisor, so it's in author papers. And he sort of pioneered these two areas. So the formal definition of malware on one side and the decidability and complexity of detecting malware on the other. Then comes his own advisor that just after published a follow-up work, interesting, without the student. Yeah? And this is a paper published at Crypto. Again, how many malware papers you find at Crypto? Not so many anymore. Very interesting work, actually. Even better from a theoretical point of view. He extended the definition that we had before to other forms of malicious code, not just self-replicating code. He called them Epeian. That didn't stick. I mean, I think virus was a good name. This one maybe a bit less so. And he also went on to actually compute the complexity class for detecting the evil. So it's not just something that is undecidable, but we can also assign a complexity class to this problem. So here now, very briefly, on, also interesting. He actually concluded that thus detecting viruses is quite intractable, and it seems unlikely that protection system predicated on virus detection will ever be successful. That was the same year, 1998, in which the antivirus industry started. So clearly, no, that was wrong. They make a lot of money. It could be something that could be made practical. But again, that was the conclusion from the paper of Edelman. So the first line of research, I try to fast forward a bit here. For a while, nothing much happened. And then in 2000, it became popular again. In particular, actually, in France, that was, Eric Fillol, Jenny Marion, etc. So we have a lot of papers here. I only mentioned a couple. on this topic of try to extend the formal definition of virus to other form of malware to make it more, comprehensive and more rich in terms of definition. Eventually, this sort of died out, though. It was still an interesting thing, and it is still. The results are very interesting, and also very interesting because the idea that came out from this line of research then sort of branched out in other fields and in other line of research of malware. So, for example, the computer immunology part by Stephanie Forrest, that is the paper that started intrusion detection, sort of started with this analogy again of computer viruses, etc. So, interesting line of research. On the bottom instead, on the complexity and decidability. So we know now that, generic virus detector was undecidable, the problem. Then we have a sequence of papers in which we actually prove that more and more things are undecidable. So, for example, is it possible to write viruses for which detection with no false positive is also impossible? Which means that also if you narrow down the problem to a single virus and not to all classes of viruses, then it's still impossible to write something that is a perfect detector. 2005, Christopher Rescus mentioned the song, went on to show that even finding that a particular behavior, malicious behavior, is inside the program is also undecidable. Not so surprising. I mean, most of the questions that we have about program behavior are undecidable. A few years later, again, we show that even the unpacking problem is undecidable. So telling whether code is unpacking is also undecidable. Okay, so here I just put a couple of this work, but sort of this line of research, was important, but not so unexpected, right? So we understand that almost everything that you ask, which is in general about a computer program, is most likely undecidable. However, here was the clever bit. It took a while, but some of these people eventually say, okay, we got it, it's undecidable. But what if we actually don't target the generic problem? We try to put constraints, okay? So if you put some limitation, things are a bit different. And here I picked two papers that I found very interesting. So the first one is a paper that I didn't know myself. I found it out when I was trying to prepare this slide. It's a paper from Spinelli published in IEEE Transactional Information Theory. Again, not a venue for malware papers in general. But it's interesting because it shows that if you actually put limits, so finite length viruses, then the problem become decidable, the detection problem, but become an NP complete. And also the paper went on and say, look, you can actually write a good detector if you're okay to tolerate some false positives, so you don't have a perfect detector algorithm. And in that case, you can actually have an algorithm that actually ends in linear time. So that was the first time that people started saying, look, I mean, you probably don't need a perfect detector first. Industry already was doing that, but academia a bit late here. And second, it says that, look, the problem is NP complete if you put some boundaries. And the other one is a paper, not from theorists here, Michael Bailey, for example, which is talking about packets again. And it shows, again, we saw the generic problem is undecidable, but if you put either a space or a time limitation that the program has in order to perform the unpacking routine, then again, become decidable and NP-complete. And again, the authors go on and say, look, NP-complete problems exist in all disciplines, and people cope with that. They just write heuristics, generic, approximate algorithms and things like this. So keep it in mind because we get back to that in a second. Last line of research that I put here in the theory part is the epidemiology. So this was the line, again, starting from the formal definition and the idea of viruses, that says that study how this virus propagates and sort of, move from one system to one target to another one. So most of this work originally was on studying graph theory, right? So you map on a graph and say how this thing propagates, and of course you make different assumptions, different works. So this was people, IBM. So IBM was on fire at the time. They had probably one of the best research groups working on malware for quite a long time because they have a combination of theory, crypto, and also practical people. They wrote a lot of these papers, actually, from IBM. Anyway, and again, in the conclusion, interesting to say that Cohen showed that actually a perfect defense against viruses is impossible. However, he said, you don't need a perfect defense. Because if you can detect a virus before, not before it propagates, but with a pace that is fast enough that this one doesn't spread, then you're successful. The infection sort of dies out. You don't need a perfect detector in general. So if you combine this one with the other one, then you get to the point that, okay, maybe industry was doing that since 10 years of this time, but maybe we can settle with an approximate detection algorithm that tries to detect something with low false positive, but in a decent time. Yeah, they say this concept of epidemic threshold of, how things propagate is perhaps the first good news that's been derived from theoretical study of computer viruses. After like 10 years of people saying, no, that's impossible, that's not going to work, etc. Now I fast forward a bit, we don't have a lot of time, but this line continued a bit. In particular, it became big again when we had the first internet worms. So early 2000, we had large infection, of course, of very fast-spreading worms. So it became, again, very important to try to model how this worm propagates. A lot of papers here, I put only one, but there are several on this topic. And then these things still exist today in the form of not too much of formal model or mathematical model of how thing propagates, but more in the form of epidemiological studies of encounters. So statistical analysis based on real data on how likely is a computer to encounter a certain particular malware in a particular setting. So this is still an open research area. So what did we learn from this part? This is not everything that happened in theory, of course. There are other stuff, Moti Young on crypto, virology, etc. But I think these are the three main lines of research that happen in the theoretical side. So what did we learn? So the biological analogy was very good at the beginning. Actually, it motivated a lot of interesting work, a lot of other research areas, but I didn't have time to enter into it. Eventually, it was pushed a bit too far. So there were a lot of papers, here I focus on the good one, but there were a lot of bad papers that tried to push a bit too far this analogy of, making, antibodies and et cetera, et cetera. Epidemiological study were big at the beginning, but then they couldn't catch up with the complexity of today's malware, spreading and et cetera. But sort of this line of research still exists, backed up by existing statistical data about malware encounters. And then we learned that everything is undecidable in the general case, is NP-complete if you put some boundaries, but we don't need perfect solution, and we can live on with actually approximate algorithm to detect malware. And that is sort of the transition between the theory and the practice. And more or less, if you saw at the beginning, most of the people writing papers in this area were people in theoretical computer science or cryptology, and then malware became almost completely a system discipline. So now we start with detection, which is the problem that we just described, and say, okay, how do we actually do detection? Keep in mind, again, antivirus company existed since quite some time at the moment, and they were doing detection. And they were doing detection by using two main methods. By using signatures, academia never liked signatures, but they work pretty well, and by using heuristics. So signatures were designed to detect known malware, heuristics to detect things that you don't know yet. So on the signature side, people start working on signature generation. How do you generate the signatures? How do you keep up with generating new signatures maybe automatically, since the new malwares, that actually were developed start increasing? It was still pretty small in 1995. So here is the first paper that discussed this. Again, sort of an obvious, maybe obvious solution. You try to take the set of malware that you try to extract sequences of bytes, in this case they consider 12 to 36, and then you try to double check those that are present in goodware, and you try to basically narrow down the choice to those that actually can be used to detect malware, but don't generate false positives. All right, interesting is this, again, IBM people, and it's interesting because they were writing paper in which they were saying that this is actually used in practice by IBM on their system. So it's interesting, right? So these were scientific paper, this is virus validated, but they were telling you things that were done actually in the real world. Then this became big again with the worms part. That is where academia really got into this topic, because here, more or less, for a while there was not much that we could do about it. But when the first internet worms starts, appearing, then the problem became very important, because we don't have time to actually have humans writing signatures, because this one spread very quickly. So here, many papers on this topic. The two probably most relevant are Polygraph and AMSA. And the idea of both papers was that, here is the one for Polygraph, is that there are certain sequence of bytes that maybe they don't appear always in the same order, they're not always in the same place, but they need to be there. For example, if you have worms, you need to exploit a vulnerability, that there may be some return address or something like this, and this is a unique byte that needs to be there. So you can always find a way to narrow down the detection to those particular parts that cannot be polymorphically modified. Excellent papers, and academia love it because then they start writing papers on, no, that's not true, and we can break it. Even the same authors start doing that. There are papers at Oakland that say, okay, we can do this, and 6 months after, the exact same author wrote a paper and say, we can evade that resistance. You probably knew that 6 months ago, but that was good. So there were a lot of papers writing in this place. Some of them that they try to pollute the data. So you try to generate signatures. What if I modify my worm in a way that use some data that then force you to generate bad signatures? And some of them, instead, that they just say that, no, it's not even true that you need this sequence of bytes that are always there. So again, not so surprising since we proved before that it's impossible to write a generic detector, but I had to go back. Second line is the one dedicated to heuristics, or model to detect things that are not known yet. So here, the first paper is this paper published in Computer Security, 1995. Not a super well-known paper, highly cited paper, though, that describe what they call telltale signs. There are these things that exist in the behavior of a program that can tell you that this is suspicious. We're not necessarily talking about malicious, since this is behavior unknown, but basically the idea is things like, I don't know, you look at the file system, it does certain operation on the file system, or it does certain operation in memory, and you say, okay, this is probably, suspicious in nature. And it could be used to detect malware that are not known. The first actually documentation of this thing is used that I could find is another virus bulletin, 1999, in which they document how these heuristics are used by antivirus company. And here you actually mention one example. For example, you have a program that immediately passes control at the end of itself, and then it looks for files on the file system. If you find the one that are interesting, you open the file, etc. So this is a class of behavior that you can use to describe a virus, for example, and that you can use to detect viruses that are not known. Nice work. Also something very funny is the fact that the paper ends by saying that that was 2000, and say now we're moving away from MS-DOS to Microsoft Windows. And Microsoft Windows is much more secure, which means that, of course, it's possible to write viruses on Microsoft Windows, but it takes more time to do that. So there will be less people doing that. And viruses will not spread as fast because Windows is more secure. So the last quote is fantastic. They say there will be no virus problem. Regrettably, there will be no such a vast antivirus market, and most of today's antivirus experts will have to find another job. That was a guy working on the field, in the industry, spot on. Yeah, Windows really solved the problem. The first big paper on the topic is, again, we mentioned before, is semantics-aware malware detection. Here was a paper in which they proposed this model to capture the behavior of a program, and then they call it behavioral templates. And then how to extract this model. We already saw before that they proved that this, of course, is undecidable to tell whether a model is in there, but they propose, some algorithms in order to find this model inside the program. What happened next? So here was the first roadblock for me to try to summarize the research, because here you find, I don't know, 500 papers on this topic, I don't know, something like this, continuing. So this is the best summary I have for you of what's going on in this area. Basically, we have a long list of papers in which everyone comes out and say, I use another model, I use another feature, I use system call, I use a sequence of system call, I use dependencies on system call, I put in a graph, I use like something else, I use, a lot of them use APIs, opcodes, engrams, everything. And then there's another paper that say, yeah, that's bad, I can evade it, I can, modify this thing and your model doesn't work, etc., etc. So a lot of work there. Very hard to summarize unless you have many, many hours. But it's interesting because at least it helps us to explore a lot of different features that we can use and to discover that most of them, according to the author, works perfectly, according to other authors, works very poorly. So a lot of stuff there. However, in this big line of work, we start understanding, this was known before, but we start, acknowledging that, sure, because we need to extract this model somehow, right? And many of them, they do it by static analysis. And of course, there's obfuscation. And so most of these papers say, what I can do about obfuscation? I need to deobfuscate, I need to be robust about obfuscation. And eventually people start saying, can't do much about obfuscation. I mean, yes, you can handle some cases, but in the worst case scenario, if something is packed or highly obfuscated, static analysis alone cannot work. You can't extract any, valuable model. So you probably need to use dynamic information. So that was, let's call it a result, in the sense that it was known, but for a while was ignored. And then there is some line of research on how to sort of make sense of this gigantic, number of papers. For example, by comparing different things, what is the right way to compose the sequence of system call or the sequence of things, etc. So try to measure that. I wouldn't say that we answer something very decisively there. And the sideline that we don't have time to explore on how to do that for botnet detection. So botnet detection was sort of a different problem because most of the detection happened at the network level, and because we can actually rely on other source of information that are not the traditional that we use for model or traditional window. Binaries, for example, reputation about endpoints and DNS data, etc., etc. So here there is a long line of research also on botnet detection. Third line of research here in the detection part is how do we actually test this model or the AD product that existed. Here I start with what the industry was doing already in the 1990s, which is very interesting, and I think we sort of forgot about it. So originally, how do we test antivirus software? It was by testing them on two data sets of samples. Those that they call in the wild, and this in the wild was actually published. There was what is called a wide list. It was published. So it was published and it would say, okay, these are the samples that are detected on real machine in the world. So you need to detect all these samples if you're a good antivirus. And then there was what it was called the zoo. So the zoo is sort of the big data set of samples that antivirus software or security company have of existing viruses, but they're not necessarily spreading. So maybe you don't find it. So actually the ones that are spreading are a very small subset of the ones that they exist. So you say, okay, here you need to detect something, but if you're not perfect here, it's not so important, because it's important is what you detect that is actually causing damage. This in academia was sort of lost. We never made this distinction really, and maybe this is an interesting idea that we need to revisit. Another interesting paper, virus bulletin, so not academic, early 2000, in which they actually describe how to test a heuristic system. So how do you actually go on and test not existing signatures, but this generic heuristic? Of course, you may think of, well, you take a heuristic from the past, you test it on sample in the future and see whether they detected, etc., etc. And again, funny enough, one of the main concern of the researcher at the end was the fact that these databases, they're getting huge. And here, I don't know what's the problem, we are already in 2000, but they were about 6 megabytes at the time. And they say, you know what? We could reach 10 megabytes. I don't know why it's a big problem to reach 10 megabytes of database for this model of signatures. But that was one of the the problem at the time. Again, MII and Somesh, some work on academic there. So this line is actually quite long, and we still didn't find a good way to test, really anti-malware or malware detection systems. So this is mentioned, for example, in prudent practices. What should you do in order to build a good data set and in order to, make sure that you don't have biases, etc. So this is still an open research direction. And as a spin-off of this one, we have the problem of how do we actually make sense, since you want to build the data set to test malware, how do you make sense of AD levels? Because AD levels is what we use in order to build the ground truth, and they're obviously a mess. So the industry tried to solve the problem. Very, 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 very long time ago, 1991, there was actually a naming convention proposed by Cairo in order to say, okay, all the AD companies should stick to this naming convention. Actually, it was more like what you shouldn't do, not what you should do, but didn't really use in practice. Mitre tried to solve the problem in another way, 2005, very good. They said, you know what, we're going to assign numbers the same way we do it for vulnerabilities. And we say, okay, you apply, and we say that this number is belonging to this particular malware family, and we have all the alias given by all the antivirus companies. So it's a central sort of repository, like we do today for CVE for vulnerabilities. Fantastic solution, never worked. I think there are like 39 assigned numbers or something like this. They gave up soon afterwards. The more relevant paper on this area is probably AV class. They use majority voting in order to try to find a label, so not rocket science, but it's the best we have at the moment. So what did we learn here? So first of all, we keep forgetting, and we wrote so many papers to show that other model can be evaded. And yeah, we knew it already. We start from the assumption that no perfect model exists and we're going to use approximate solutions. So probably it's useless to write so many papers to say that that model is possible to evade. We try every possible model, every possible feature that can be extracted. Eventually, we agree that static models, they're difficult to apply in practice because if you have, complicated obfuscation or packing, they're very difficult to apply. They could still be applied if you use instruction extracted at runtime, but extracting instruction at runtime is typically very costly. Doing not at runtime, we know it's limited, okay? And overall, I would say that we still don't know exactly what is the right way to test these solutions. So maybe we should go back also with this idea within the wild. But yeah, we have a lot of recommendations nowadays, so we avoid common errors. But still, there are a lot of things that we don't know how to do. Or at least, let's say every researcher does in a different way when they need to test their detection systems. Now we move to the last one, which is ML. Dedicated line, because here we could make like an entire course about it. So, first thing, interesting, first paper that used machine learning for malware detection. This is 1995. It's a very long time ago, actually. And this is called Biological Inspired Defenses Against Computer Viruses. You will not tell that it's machine learning related. Again, from IBM. And described actually a neural network to detect boot sector viruses. So that was really machine learning. I mean, the neural network was not very sophisticated, and mainly they were using trigrams, and they were saying, look, we don't have enough data to train a lot of hidden layers, so it's going to be pretty shallow. But, well, it's a neural network to detect this. And it was actually used by IBM, so it was a real solution. We had to wait until 2000 in order to find the first approach of this applied to PE files. So that one was a very particular class of malware. Of course, boot sectors, the boot sector is always the same size, very limited, etc. So then they extended to PE files. It was a bit more complicated. They tried with 3 grams and 4 grams, and then they used a sort of voting system where the more network could detect something. So not really what we would do today. But again, it was sort of there, and it showed you that, this is something that they could use in practice in order to detect things mainly that were unknown. It was already clear at the time for the industry that this solution were not to detect malware. For detecting non-malware, you have signatures. But to detect things that are not, or there are variation of what you know, these systems seem to work relatively well. Yeah, they already explained things, etc. They were saying that, we will really need a lot of viruses in order to train more hidden layers, like, at least 128 variation of something. So the numbers were very small at the time, but, the theory was there. Yeah, and here's what I say, that they were clearly already explaining that you use expert design heuristic, and, this is only to complement those one in order to detect something else, not to replace. Academia sort of forgot about that. Then we have one of, very big papers about, trying really machine learning to detect malware. This is by Stolfo. And in here, they try different approach. They try different, classifier. They try different features. Different classifier, they were on different features, so they didn't try all the combinations. But they find out that, some of them, in particular, the one that use n-grams, perform better. Look at better, accuracy is 97%, and false positive was 4 to 6%. Which you say, well, nowadays you'll say, that's probably not very good to be used in practice, right? But this was realistic, I would say. That was sort of realistic results. And it was maybe the first and the last paper with the realistic result for a while. Next, we got the first paper. This is one-off, but, very famous paper, published in KDD, in which they show, look, 4 grams only, we experiment with other classifier, decision tree, and what we get is a perfect 0.996 area under rock curve. More or less problem solved. If you wake up from cryogenesis and you read these papers, you say, boom, malware is solved, malware detection is solved. Was that over? No. Here we get the big one. So starting from more or less early 2000, maybe 2005, we got like a lot of papers, mostly not in security conferences, mostly by machine learning researchers, that they try everything that they had. Anything that they try with something else, they just try. They reuse also the finding of the previous line of research, like we know how to extract features to build this model. Let's try every possible feature. So every possible combination with every possible feature. And most of the time, they get 0.99. This is a nice picture. It's actually from a survey in 2020. And this is only for Android malware. And this shows you, the different papers on the different, they use the different classifiers. So as you can see, they more or less cover the entire space. Try everything on everything. And this is only for particular case of Android malware. More or less, this paper reads like this, right? So we take a set of malware, often a bad one. Then we convert samples to numbers somehow, or pictures or whatever that can be digested. We don't care too much about whether this makes sense or not. Then we take a classifier that was designed to detect something else, like images of cat. And we feed it with this data, and we get very high accuracy. And if we don't get very high accuracy, we go back and we remove something from the data set, for example, packet samples. Packet samples are hard, so let's get them out. And then you get 99% accuracy. Maybe I'm a bit too critical, but this is what I call sort of the dark ages of research on machine learning and malware. And it was mostly due to the fact that security people didn't know machine learning, and machine learning people didn't know security. And so there was a lot of garbage that came out of this. Not everything was garbage. I'm simplifying a lot. There were very good papers that came out of this period. I don't know, Konrad Rieck in Germany wrote very good papers, for example, on machine learning and malware. But there was a lot of noise that came out of this. Give or take, my message is that this dark age lasted about 10 years. And after 10 years, more or less, system people learn a bit of machine learning learn a bit of security, they start forming groups together, and we start having good results and good papers out of it. So again, here summarizing the rest is going to be very hard, but I just give some example of lines of research. So first of all, we have some papers that look back at all this data and say, guys, you made obvious mistakes there, right? One of less known is actually from later on here, published by ASOS, very good paper. I don't know why it was published there. He actually mentioned two important things. So he mentioned the problem of temporal consistency, which means that you shouldn't use information that comes from the future when you do your random sampling for training and testing. And he also mentioned the concept of concept drift, that then became both big line of research in the malware space. And later on, we have another paper, also at DIMBA, published at DIMBA, another fantastic paper. A lot of people don't know it because they published it at DIMBA, but you should read it. And here the author again covered two things. They discussed the temporal label consistency. So not only the problem that samples were coming from the future when you put in your training data set, but also the fact that labels change over time. And if you use the label consolidated 2 years after, then well, those were not available when you actually could do the training of the data, and that also pollute the results. And also shows a very interesting experiment in which they use real humans in order to make selective classification of few samples per day. And they show that if you use this one and you put it in the loop with machine learning, that really boosts the performance. Because sort of when you have particular difficult cases, if you can ask human to give you ground truth for that, then you can actually use this to improve the system. So very interesting work on that area. All right, so then we go to the paper not paper on adversarial for malware detection. So this was a paper that, again, not so surprising, but mostly talk about two things. It says, well, so we can take machine learning classifier and we can probably evade them by creating adversarial samples. That's what we were doing with, images and, and audio, etc. And then they show that you can make the classifier more robust if you actually use, well, they tried two different techniques, distillation and adversarial training, and they conclude that mostly adversarial training actually works in order to make the system more robust to the same adversarial, of course, samples, which again is also surprising, right? So you can evade the system, yes, if you can transform the samples, and yes, if you train on those sort of transformation, the system gets a bit more robust. And this starts another, crazy sort of line of research in which everyone say, you know what, I'm going to write another paper in which I show you that model, I can create an adversarial sample and evade it. And yes, of course you can. That was there, it was obvious, but that doesn't stop people to keep saying that. This is sort of a very short, if you see here, line, but already in 2021 we have the first ACM surveys on the topic, just to give you an idea that this was already big. And then there was another survey in 2023, IEEE survey on this topic. So this is, of course, very big. So this is one from one of these papers, the list of all the adversarial samples, how they generated, etc. Big line of research, sure. I would say most of these results are relatively obvious in the sense that, yes, you can evade a classifier if you generate sufficiently different samples. So I think here the main question is, what does it mean, manipulation? What are you allowed to manipulate? What you're not allowed to manipulate? That was very clear in the image domain. The cat remains a cat. Humans can see it and say, that's obviously a cat. You tell me it's a balloon. Well, you're wrong. But here we don't have an oracle like that. So if you change a computer program, what does it mean change a computer program? People say mostly they agree that what you should preserve is the behavior. But again, I'm not super convinced. Of course, you need to preserve the behavior, but that's enough. What does it mean? If I rewrite a program complete in Python and I preserve the behavior, that's a valid transformation. Well, good luck having a static classifier that can detect that. I mean, obviously, here is a bit more fuzzy and the boundaries are a bit more unclear. Then we have a line of research, I mentioned two papers here, that is also very interesting, that looks at statistical model in order to detect the problem we described before. For example, yes, you can create a adversarial sample that evades a classifier, but most likely this adversarial sample will look pretty weird. Right? So maybe we don't need a classifier that can detect it, but we can simply pre-filter and say, look, what is the hell is this program? So if it's too weird, maybe it's an adversarial sample. So this idea of using statistical measure in order to tell whether someone went a bit too far in the transformation, I think is something that is a powerful idea that maybe needs to be explored a bit further. Another thing that happened at the time, this was a paper I wrote, and that's why I mentioned, is that as a researcher in the field, this was the time in which we started having actually the first product that they say we can detect malware using machine learning, using only raw bytes. Feed us raw bytes, and works very well. As a researcher in the field, I thought, yes, that's impossible. I mean, we studied this for 30 years. I mean, of course, there is obfuscation, there is packing. You can't do that. So we went on and we tested. And actually, it worked. And it was a big surprise. And I said, how does it work? And it did work. And it did work because what we find out is that packing, even as an idea, is perfect. As an implementation, is not. So there are parts of the file that are typically not covered by the packing routine. And what the machine learning classifier learns is basically how to identify this part and try to build a signature for it. So we're using a very opaque, very black box system. And what it does is just build signatures for these invariant parts of the file. This works well because there are no perfect, well, they can be, we show in the paper they can be, but in practice, packing and obfuscation is not perfect. And so you can actually build this. And in presence of good instead packing, then what the machine learning learn is basically nothing, or you just learn to tell packet or not packed apart. Another paper we did here with you, also in the room, was to compare what humans and machine do when they classify malware. And again, here, was not what we are expecting, but one of the things we find is that human and machine are equally good. So machine learning classifier can tell apart more or less, with the same precision of experts, but we look at completely different feature set. And that's interesting. And in particular, it's interesting why humans are able to classify malware almost exclusively using dynamic information, while machine learning classifier, they tend to avoid using dynamic information as much as they can. And if you force them to use them, they typically perform much worse. There must be something there. Actually, obviously, we have several ideas of what it can be, and probably it's a combination of all these ideas, but it's something that we don't have completely clear in mind. And okay, more work on this. The first paper that started coming out also last year on studying the concept drift and trying to tell why we get concept drift, what is the part that actually caused the concept drift. It's still also early. There is another one that came out, 2024. This is definitely an area of research that probably will get more paper in the next months already. Okay, so that's the general picture. So what did we learn about the machine learning part? The first part is the same, because again, we keep doing the same mistake. We forget that this is not a perfect detector, and we spend probably too much time writing paper to show that, yes, I can evade this detector. Of course you can. Then we learned that most of the experiments that people did, at least in the 2005, 2010, 15 area, were done on data that was not really correct. So they used data that was not representative. They only used few families. They only used few samples. They were using data from the future to train classifiers. They're using labels, etc. So all possible type of mistakes. And we try to actually now document this and tell people, okay, you should probably do this way and not make these mistakes. We learned that adversarial sample can break everything, and if you do adversarial training, you can make everything more robust against that particular class, of course, of transformations. And we sort of learned that, using system calls, dynamic behavior, to train and then detect malware doesn't work as well as we hoped. And we still don't know why, so I'll talk about that more later. And and then the packing part that I already mentioned. I'm very late. So I will speed up. That's the last one. So we talk about detection. Now we have analysis. I go a bit faster on analysis in the interest of time. So analysis as a research domain came out later than detection. It's kind of weird because first you need to analyze and then you can detect. But the point is that analysis was done manually. Every security company had, their red team, malware analysis that basically look at samples and reverse them, and then they write signatures. So this became a big research area at the beginning of 2000. And this was mostly motivated by scalability, because we have too many samples, so you need automated system in order to do the analysis, to collect the data that you can use for your classification to build signatures, etc. So early 2000, we have the first set of papers describing what we now call malware analysis sandboxes, which became the tool to basically perform dynamic analysis of malware. So we had TT Analyze that became Anubis, was based on an emulator, so inspecting the machine from outside the machine itself. We had CW Sandbox from Thorsten, in which instead they did, the instrumentation inside the VM. And then we had Panorama that was, again, based on emulator, that was using a whole system pain tracking in order to, more sophisticated, in particular for privacy breaching malware, so when you exfiltrate data, etc. But these two became like, the first standard, let's say, in terms of designing virtual machine, sandboxes for analyzing malware. And starting from there, the research branched out and became quite broad. So we had a line of research covering the design space. So how do we design these sandboxes? What is the best way? What is the trade-off of different choices? Then we have one line of research focused on repeatability. I will not call it a line because there's probably one or two papers, but then there is one on stimulation. That is, okay, you do dynamic analysis, so you need to stimulate the program in order to actually observe the behavior. How do you do that? What is the best way to do that? And finally, there is a big one focusing on evasion and countermeasures. Like, okay, now we knew how to obfuscate program and pack program against static analysis. What can we do against dynamic analysis? There's all classes of, evasion that you can do. They're much actually easier here. You can just, for example, wait and don't do anything for an hour or things like this. So there are different classes, and we need to study them, classify them, see what we can do about them, and etc. So, quick on the stimulation part. On the stimulation part, we have two sort of line of research. We have first paper, which is one or two, which basically describe how to force a binary to execute multiple paths. So multiple path exploration was called. The other line is how to use symbolic execution to explore different paths. This line didn't really quite work in practice. The first work on it is BitScope, that then became BitBlaze, part of the BitBlaze. There are some other works more recently, but it's not widely used. This one is not widely used either. Sort of works. I did implement it, in particular case, you can make it work, but engineering-wise, it's super complicated and it's extremely, extremely slow. So both lines are still sort of not really at the maturity that can be used in practice. In terms of trade-offs, there are a lot of papers. Here I put a couple of examples. So there are those that explore different ways to design sandbox, use bare metal, for example, use out-of-VM instrumentation. How do you use out-of-VM without an emulator because it's too slow? How do you, etc. Many papers on this area. There are papers that just explore individual, choices. For example, with ROD1, seeing how long do you need to run a sample in order to collect data. There are other ones that look at, different features that can be tuned in the sandbox in order to collect better data. On the evasion side, the first paper I could find of anti-evasion for malware dynamic was Cobra, which was not really on sandboxes, was an Oakland paper. But then the research almost completely moved under the sandbox part and say, okay, how do we build, evasion-resistant sandboxes? So here again, probably 100 papers, different line of research. There are those that focus on countermeasures. There are those that focus on detection. How do you detect that a malware is not behaving correctly because it's detecting the sandbox? And there are those that that focus on proposing new evasion techniques. And then other papers pick up and how do we detect them. But in this case, this sort of, arms race is useful because it helps us to build better sandboxes. And there are those papers that instead focus on measuring. Like, how do we measure the prevalence of this technique so we know which one we need to address the most or more urgently inside the sandbox? So many papers, I try to put one or two examples each year. Repeatability, largely unexplored. It's a big problem, we all know. Like, you run the samples today, someone else run it in like 3 weeks and it doesn't work anymore, or it gets completely different results. How can we, repeat experiment or build a system that can be used to repeat experiment in the future? One fantastic paper on this topic. But the paper is a DIMBA paper, but it's actually the one that used Panda in order to build a system based on record replay that can actually record the non-deterministic state of an entire operating system and then replay it deterministically so you can re-execute the same malware multiple times and get exactly the same execution. That solves a lot of problems. Solve the repeatability problems, solve the problem that you can build analysis routine that are very slow because you don't need to do the analysis when you actually run the sample. You can do it when you replay it. And at this point, the time is fixed. So you can go 100 times lower and the program still behaves exactly the same. So fantastic. It solves also partially the containment problem because when you rerun it, everything is faked. So you actually talk to the network without generating network traffic. So fantastic papers. The problem is, of course, there is a catch, is that it's a bit slow. I will not say that that's the showstopper, though. Yes, executing something under Panda to do the recording goes slower, of course, and then you need to repeat the execution in order to do the analysis. But then also storing the recording takes some space. It's not huge, again, on order of megabytes, because it's only the non-deterministic part of the input. But still, if you want to store this for millions of samples, that's obviously a big problem. And so, yeah. And then we have the line of clustering. I don't enter in the clustering too much because it's another big one. And here is, again, unsupervised learning, how to try to find a way to put together things that looks the same because that can save us time not to analyze other things, or because that can be used in order to tell to which family a certain sample belongs to. There are many papers on this topic, some very good ones, some less good, and more or less it follows the same line of we saw before. First paper saying, I do the clustering that way, then other come and say, can't do that way, that the result will not be correct. You need to measure in a different way. I tried myself to do clustering many, many times, and I almost always fail. This is one picture I got for one of my papers in which clustering actually worked. And what I learned is, in 2 words, is that clustering many malware samples might work if you have the right conditions. So right condition in this case, this was for IoT malware. IoT malware is not packed. So if something is not packed and you can look the code, you can use the code as a source of information, then things work pretty well. If you have packed samples that you cannot extract the code, by clustering using other means, network, dynamic behavior, things like this, almost always got completely weird results. Maybe it's just me, but difficult problem and still open. So what did we learn here? We designed a lot of different types of sandboxes, but I think we made progress. So if you install a sandbox today, they're pretty well designed. They already provide a lot of features for anti-evasion. So we sort of learn, and we learn well the trade-offs of when you want to use bare metal versus a VM, you need an emulator only in particular cases, etc., etc. We study a lot of different evasion techniques. We try to measure how much I use. We try to, incorporate this information in the sandboxes itself. We learned that, for example, it's probably 2 minutes are probably enough to run a sample. If you go over that, you probably don't gain a lot. If you do 5 minutes, 7 minutes, a lot of people did that. We saw that we, really don't get a lot of gain. Multi-path exploration remain impractical in most cases. So all approaches that have been proposed, they sort of work in some cases, but they're not scalable. They're can be really used on a large scale. Clustering, I don't know. I told you what I think about it. Fund is fantastic, but is not. It should be used more. Probably you use it in many papers, but then you throw away the stuff. So I don't know. Building a good data set based on Panda. The authors tried. They have online samples, but not enough, and so it's not used a lot for that reason. And finally, we don't have efficient triage technique. I didn't talk too much about that, but that's important. And that sort of comes from the clustering part, which means that we don't have a way today to tell whether a new sample that we analyze, which we detect to be malicious, is an interesting sample, which means it's a new malware family, for example, or it's just a variation of what is known. On this topic, there are only a handful of papers, maybe 5, 6 papers in total in history. It's a difficult problem, but I think there we should probably do better. All right, I ran a lot, but this is more or less what I cover. And this is what I didn't cover, which is much more. But there are a lot of other lines of research, of course, that they spin off from different parts of these jobs. Interesting, some of them are very big. I didn't talk about mobile malware in general, etc. But I try to cover at least the 3 main problems that researchers try to address and the question that they try to answer in these 3 main large areas. And now to finish, 1 minute, is I give 10 open problems that I think are interesting to explore. There are many more, but I have to pick 10. First one is triage. I really think that we should do more on that. It's very important. How do you tell whether a sample that you analyze is something that requires maybe humans to look at it or something more in depth? Machine learning, never almost used there. Maybe can play a role. It's been used in the form of clustering, of course, but we saw the clustering has a lot of problems. So what can we do better there? The second, I also already mentioned it. Human favors dynamic features, and they do well with dynamic features. Machine learning doesn't. Why? Because we don't do feature encoding correctly, because we don't, because we use a lot of semantic information that the machine learning doesn't know, because there is obviously also the sparseness of the problem, like network traffic, often you don't see it. So maybe the machine learning doesn't like the fact that features are very sparse. I don't know, and probably all these things play a role at the same time. But if humans do well, we should be able to teach a machine to do well as well in this area. I didn't talk about that, but that's also in the analysis part an open problem. What do we do about what they call implants? I don't know if you're familiar with that. This is something that became popular with the NSA leak. Basically, the idea here is that you use malware in order to infect, for example, the firmware of the hard disk. So if you infect the firmware of your disk, then the disk is infected. It can keep reinfecting your system, you can reinstall the operating system, doesn't matter. You cannot detect it because even if you try to extract the firmware, well, the infected firmware will give you the clean firmware out. So you need to sort of open the disk and take it apart to extract the content and see. So that's a scale, can do it. You can even scan whether inside your computers you have such a thing. We don't know if you extracted how to analyze it. So this thing is sort of put it under the carpet and no one talk about it because big problems, we don't know how to solve. Another one for detection. I believe that we still don't understand quite well what is the overlapping between the different techniques. So we have signatures that we still use in practice. We have heuristics or some sort of models. We have all the machine learning classifiers. How do they play together, right? So is it still the case as it was proposed 20 years ago that machine learning should only complement and signatures should be used to detect known samples? Is the machine learning replacing the signatures? Is it learning signatures eventually, so they actually do the same job mostly? I don't know. I think the way this thing overlaps and they replace each other and never been quite understood and studied a lot. Containment, elephant in the room, in my opinion. So every time you talk about dynamic analysis, well, you're executing a sample. The sample could do nasty stuff online. Right? So you should contain it. You should make sure that it doesn't do bad stuff. That's more or less, this is the requirement, and this is the technical thing, right? So everyone will tell you, you need to do that, obviously. And every company will say, of course, we do our best. That's it. No one really says what you should do, because clearly, if you don't give internet access, malware doesn't run. If you give internet access, well, nasty stuff can happen, and they do happen. There are people that submit to sandboxes online samples that just they use as a trampoline to execute attacks on other systems, and they work. So I don't know. There are maybe 1 or 2 papers top in this topic so far. It's a big problem, but we should probably study it a bit more. The other one is related to the different platforms. So we have MS-DOS and then Windows malware. We have mobile malware, we have IoT malware, and we have papers written, tons of paper repeated in the 3 different domains. But we have key results also that came from one of these domains. For example, in machine learning, often people use mobile malware as a data set, but doesn't mean that the results that we got is transferable to a certain extent to other domains. So what we learn about testing on, Android, can we say that that's true in general about malware also for other platforms? Maybe not, maybe yes. How the different platforms actually affect the evolution or the detection of the different malware. I think we have a lot of paper on the 3 separate. We don't have a lot of papers that try to put this thing back together. Number 7, well, LLMs, I had to put it there. This will be probably one of the first one to make another graph of mess. So what can you do with LLM? Obviously, you can use it to explain reports, maybe enrich features, maybe obviously generating variants of malware for adversarial training. But what else? What is the one that is sort of the killer application for ML and malware? Concept drift is another one that I believe would be sort of solved first. Is we understand that we have the first paper coming out now this year and last year to study more concept drift. But I think there are still open questions like which features are more affected and why. Is it better to use this feature? Maybe you would get a lower accuracy. How do all these things play together? I think is something that we need to figure out. I had to put one theory question, not my area theory, but I have one. What does it mean that something is hard to evade? Maybe it's not theory question, but actually, but that always bothered me. So there are so many papers that say, we know that everything can be evaded, and then another paper come and say, oh, I was able to easily evade that one, and another guy say, well, now I raise the bar because I do this one is harder to evade. What does it mean it's harder to evade? I mean, is it like I changed 3 bytes and now I need to change 500? It means it's harder to evade? No, it's not. It's still automated, right? So if now my classifier is harder to evade, but I can still automate the fact that I can build an evasion thing. Is it really harder to evade? I don't know. I think we need a measure of what does it mean to raise the bar. What is really harder from an attacker to do? Because, I don't think we have this measure. And the last one is I still don't think we have a clear way of how to combine static and dynamic. So we know the static have limitation. We have the dynamic have limitation. We say that we should use dynamic because the static could be easily fooled by packing. But then we say, okay, we use all together. But all together, we saw in experiment, it doesn't work very well. And he has a drawback on relying on dynamic, which is costly all the time. So maybe we need a better way to build a pipeline and to try to only use dynamic when it's needed, only when it's reliable. I don't know. But the right way to combine the two, I think, is also something that we have not enough paper looking at so far.